Log on, tune in, find out. Another good idea from Cambridge.
Afternoon is by Ján Pich from Charles University in Prague, and it's about hard tautologies.
Thank you. First of all, I'd like to thank the organizers for inviting me. I'm interested in proof complexity of P versus NP. As you might know, there are several results in computation complexity stating that certain techniques cannot resolve P versus NP, like relativization and algebraization or natural proofs. In order to understand these barriers better, it seems useful to consider corresponding formal theories. Like, for example, a theory T is such that whenever T solves P versus NP, the solution relativizes. This theory should be as strong as possible and somehow nice. For example, it might be a fragment of piano arithmetic so that we can easily measure how strong it is. We actually already have some theories of this kind, so using these barrier results, we can show that certain theories can't solve P versus NP, and then we can try to extend it to stronger theories. In this presentation, I would like to concentrate or focus on the probability of circular lower bounds. Interestingly, using known translations between further logic and propositional logic, the probability of circular lower bounds, the unprobability results here in further logic correspond to hardness result of propositional formulas in propositional logic. Roughly speaking, we can translate any universal statement of this form for all x ax, where A is a finitistic sigma b0 formula A, into a sequence of propositional formulas A1, A2, and so on, where An expresses validity of A on inputs of length n. So the sequence encodes the same fact as the original universal statement. Moreover, when a given further theory and the propositional proof system are properly designed, the probability of this universal statement corresponds to efficient probability of this sequence of propositional formulas in the corresponding propositional proof system. And the circuit lower bounds can be expressed as sigma b0 formulas, so the unprobability of, say, superpolynomial circuit lower bounds is often obtained by showing hardness of propositional formulas encoding circuit lower bounds. Perhaps the most interesting barrier in this context is the one by Rasbarov and Rudic, natural proofs. It says that if strong pseudorandom generators exist, then there is no P-poly natural proof against P-poly. Where P-poly natural proof is any proof such that it implies that there is a set of Boolean functions C, which is useful, meaning that any sequence of functions from this set C is hard for P-poly. It is hard, so for any number of functions on n inputs in this set C is big, and it's constructive, so meaning that whenever you are given function f represented by its truth table, you can efficiently decide its membership in the set C. Importantly, Rasbarov and Rudic also showed that all known circuit lower bounds on restricted classes of circuits for explicitly defined functions are natural. So this is like considered as a big barrier. And for us it is interesting that it can be used to show that a theory of bounded arithmetic called S22 alpha doesn't prove superpolynomial circuit lower bounds unless strong pseudorandom generators exist. Here S22 alpha is a fragment of piano arithmetic with a form of polynomial induction for sigma b2 formulas, sigma b2 alpha. I don't want to go into details of this result because I think that it is much easier and much more convenient to work in propositional setting here, where using basically the same kind of proof, the same trick, we can show that no propositional proof system admitting feasible interpolation proves superpolynomial circuit lower bounds efficiently for any function f, where superpolynomial circuit lower bounds are encoded, formalized by these big disjunctions of this form. Here function f is represented by its truth table, so this is formula using like 2 to the n number of variables. And the size of the circuit C is Tn, where Tn is any superpolynomial function. So by the hardness of superpolynomial circuit lower bounds, we mean that for any superpolynomial function Tn, it is hard to prove that given function f is not computable by circuits of size Tn. Now I should define what is this feasible interpolation. We said that the propositional proof system admits feasible interpolation if whenever there is an m-size proof of ax, y, or bx, z, where x are the only common variables of a and b, then there is a poly-m-size circuit such that for any assignment a to the variables x, the circuit C can decide which of these disjuncts a or b is true. It is known that proof systems like cutting planes or resolution admit feasible interpolation. So we have this kind of improbability results, but it wouldn't be fair to say that S22 alpha or feasible interpolation somehow captures the essence of natural proofs, because strictly speaking, any proof of anything might be natural. So the main question here is whether we can extend its results to stronger theories, like, for example, Frege systems. These are usual propositional proof systems based on finitely many derivation rules, like, for example, this well-known Hilbert calculus. And they are considered as, these are very strong proof systems. The problem here is that for these systems we don't have feasible interpolation. For example, it is known that if an extended version of Frege system admits feasible interpolation, then RSA is not secure. So here probably a new technique is needed. Currently we don't have any non-trivial lower bounds for this kind of systems. It is actually even hard to find a good candidate hard tautologies for these systems, but circuit lower bounds seem to be quite reasonable candidates. Actually, there is a conjecture by Rasborough, which roughly speaking, implies in its full generality that superpolynomial circuit lower bounds are hard for Frege. And roughly speaking, it says that for any string b, Frege doesn't prove efficiently that b is outside of range of any NV generator based on p-poly function, which is sort of hard for NC1 circuits, and where A is a suitable combinatorial design. Again, I don't want to go into details here. I just want to say that we know that this conjecture holds in some form for systems with feasible interpolation, and it implies hardness of superpolynomial circuit lower bounds for Frege. It's probably even more interesting that Rasborough, using these NV generators, Rasborough also obtained that proving superpolynomial circuit lower bounds is hard for resolution log n. This is a resolution working with log n DNF formulas. And it is known that for this proof system, res log n, we don't have feasible interpolation. So this is currently the strongest hardness result for circuit lower bounds of this kind. Okay, so this is one interesting direction of research, but I would like to continue with a different approach. I think it is interesting to consider sort of weakening of feasible interpolation called feasible disjunction property. The reason is that there is an attempt by Rudic to extend the natural proofs barrier. He showed that assuming that there are so-called superbits, there is no NP-poly natural proof against P-poly, where NP-poly natural proof is the same thing as P-poly natural proof, but the constructivity condition is weakened to NP-poly. So designing membership in the set C in this NP-poly natural property is allowed to be in NP-poly. And superbit is an interesting thing, sort of a pseudo-random generator for hard for non-deterministic circuits. More precisely, for a p-poly function G is a superbit if for any non-deterministic circuit C of sub-exponential size, this inequality holds, which is a little bit confusing. Here the order of probabilities is very important. If we had the absolute value of this left-hand side as it is usual in definitions of pseudo-random generators, a non-deterministic circuit could easily guess the right SIP X of this generator and break it. But with this order of probabilities, it is somehow forced to find out when the given input Y is outside of range of this generator G. So this is...
Sorry, the difference from the pseudo-random generator to allow this non-deterministic circuit.
Yes.
And you're saying about
Yes. So the assumption that superbits exist is stronger than say that NP is not equal to QNP, but it would be still surprising if it didn't hold. It's interesting that it's actually a trivial consequence of theorem by Rodic that if superbits exist, then for any propositional proof system P, there is a function which is hard for p-poly. Actually, a lot of such functions, such that this proof system doesn't prove that F is hard efficiently. So here we have formulas that are hard for all proof systems, but this is not sufficient for us because we need F to be a specific function, like for example SAT, or at least something that is clearly explicitly defined. Here again, this NP natural proofs can be used to show that assuming superbits, there are non-propositional proof system with feasible disjunction property this time proves that proves superpolynomial circuit lower bounds efficiently. And here we say that a propositional proof system admits feasible disjunction property whenever there is an M-size proof of A or B, where A and B have don't share any variables. Then there is a poly M-size proof of A or a poly M-size proof of B. So we don't need to construct this proof of A or B. It is sufficient that it exists. Right now, I think that we don't know any propositional proof system which would admit feasible disjunction property and wouldn't be known to admit some reasonable form of feasible interpolation. But on the other hand, there is also no any negative result like with feasible interpolations, so maybe we don't need to break RSA to show that Frege admits feasible disjunction property. In this context, it is probably interesting to mention intuitionistic logic. If I'm not mistaken, one of the original philosophical ideas behind intuitionism is a sort of feasibility requirement that whenever you have a proof of A or B, you can derive A or you can derive B. I guess that back then people couldn't consider feasibility in terms of modern computation complexity. So today's intuitionistic systems don't admit feasible disjunction property or don't take computation complexity into consideration, but maybe they should. Maybe they should be formalized in such a way that they should admit feasible disjunction. It is not completely ruled out that they actually do admit it, but it doesn't seem to be obvious, at least. Some people like Buzz and Mintz already considered similar questions, and they show that intuitionistic sequent calculus for propositional logic admits feasible disjunction property. And later, Pavel Pudlak extended it to feasible interpolation property. But here, the translation between first-order logic and propositional logic doesn't work so nicely. So, for example, I don't know any first-order theory which would correspond to intuitionistic Frege. Therefore, it seems that if we want to understand our barriers properly, we need to work again in first-order setting. And in case of predicate logic, Baz and Mintz constructed a counterexample. They showed that there is a sequence of disjunctions with polynomial size proofs, such that there are no polynomial size proofs of disjunct AI. But in their counterexample, the number of quantifiers in AI grows up with n. So for us, in order to prove unprovability of circular lower bounds, it would be sufficient if we had just a kind of feasible disjunction where where the complexity of disjunctions is very fixed. So I find it interesting to consider possible formalizations of intuitionistic systems where some forms of feasible disjunction property hold. And I should also mention another interesting thing that occurs in the theory of intuitionism, the sort of conservativity, which works in a very general way. And in our case, it is interesting, for example, that S12 theory, a very strong theory of bounded arithmetic corresponding to extended Frege, is for all sigma B1 conservative over intuitionistic S12. This means that whenever you prove superpolynomial circular lower bounds in S12, you can do it constructively in intuitionistic S12. So on the one hand, if you can show the unprovability of circular lower bounds in these intuitionistic systems, you will obtain very strong result, unprovability over this S12 theory. But on the other hand, it also says that it is probably a very hard problem as well. But still, maybe this intuitionistic logic reveals some inner structure of proofs, and you can see better, you can obtain some computational information from this, so it might be useful. So I found this thing is interesting, and I think that's all I wanted to say, basically. So thank you very much for your attention.
Yeah, thank you very much for your nice talk. And I would like to open the discussion. Are there questions or remarks?
Very technical question when in these theorems of Bas-Mintz and Black, intuitionistic sequence calculus refers to propositional logic.
Yes.
Right? Not first order or higher order.
Yes.
Can you recall what the Frege system is?
Yeah, so roughly speaking, it's a propositional proof system which is based on finitely many derivation rules that you can apply on any formula.
So is that a fixed system, or is it sort of a type of systems that you allow when you say
It's type of systems, but it's known that they stimulate each other polynomial. Like that when you can, for example, you take two Frege systems, two different Frege systems, then if you prove phi in the first system, then you can find proof in the second system, which is only polynomially longer.
Oh, and this was sort of the basis for one of the Frege systems, also the Hilbert system, or what?
Basis. This is the Frege system for Hilbert
Yes.
protocols. So this is one of them.
Mm-hmm.
This one simulates all other polynomial.
Further questions? So we thank our speaker again.